This is my version of the Drake and Kahn equations. I call it the Jackson equation. And what it does is it calculates the number of communicating civilizations in our Milky Way galaxy. And we will take this term as the average lifespan of different star types: F stars, G stars, K stars, and M stars. So let's start with the equation. It is estimated that there are at least 100 billion stars in the Milky Way galaxy. That could be more, it could be as much as 400 billion, but let's be conservative and say 100 billion. The fraction of those stars with planetary systems. We know from Kepler data that that is a very large number. Most stars have planets. That number should approach 1, so let's say 0.99. And the fraction of those planets with an environment suitable for life. Let's say that over 1 in 5 will have an environment suitable for life, 0.22. The fraction of those planets on which life actually appears. Some astrobiologists say that life should arise quickly on planets. Others say it could take a long time, if at all. So again, let's take a moderate view on that and say half. So half of those planets on which life actually appears. And the fraction of those life-bearing planets on which intelligent life appears. Let's be conservative and say 1 in 10. That may be optimistic, maybe conservative, I don't know. There is no right or wrong answer for this. And the fraction of those planets on which intelligent life emerges, develops a technology that releases detectable signals into space. Let's say if you're intelligent, then eventually you're going to have radio astronomy and radio broadcasting, and we'll make that half. That may be conservative, maybe optimistic, I don't know. F-type stars. F-type stars last on the main sequence for about 4 billion years. If intelligent technology develops in 3 billion years, they'll have plenty of time to send detectable signals into space. If not, it may take longer. Chances are they're not going to last as long anyway, so let's make that a small number, 4,000 years. G-type stars, like our Sun, we orbit a G-type star. It's a G2V star. I hope that we're going to be around for a long time releasing detectable signals into space. That could end quickly through global warming, war, or even a cosmic collision with an asteroid or a comet. Let's say that that's 10,000 years for G-type stars on average. And K-type stars can remain on the main sequence for around 60 billion years. Now, the age of our galaxy is only 13.2 billion years, so I use that as a max. Therefore, the chances are that any civilizations orbiting K-type stars are going to be longer lived than a G-type star system, for example. So I'm going to say 15,000 years for K-type stars. M-type stars can remain on the main sequence for over 100 billion years. Again, the age of our Milky Way is only 13.2 billion. So let's make that value 75,000 years that they're able to release detectable signals into space. Chances are M-type star civilizations are going to be longer lived. Let's click estimate for N and see what the result is. F-type stars, we have 544.5 civilizations orbiting F-type stars. G-type stars, again, that's 544.5. K-type stars, 618.75. Civilizations orbiting M-type stars, there are 3,093 according to our estimate. And we add everything together, and we get a total of 4,801 civilizations whose electromagnetic emissions are detectable. and that makes the average distance to the nearest communicating civilization 516 light years. Here's how we arrive at average distance. You take the volume of the Milky Way, divide it by n, which is our number of civilizations using radio, and you cube root that value to get d, the average distance. Here we have some candidate stars within 50 light years of 516 light years, our estimate for the average distance. Here's Kepler 186. It's an M-type star. It's on the main sequence. Its distance is 492 light years away. Kepler 186f. This planet is comparable in size to the Earth. We can probably get a good picture of the comparable size, an artist's rendition from Wikipedia, and here it is. This is the Earth, and here is the size of Kepler 186f, and it is in the habitable zone, so there's a good chance that there may be life, and there is another chance that there may be intelligent life. The distance is 492 light years. This image was taken from NASA Eyes on Exoplanets program, and you can download this program at this URL. I'll provide the URL at the end of this video. It's a very good program. You can actually see these orbits in action. I recommend it. And that is the Jackson equation. Oh, by the way, I wanted to say it will take another 428 years for any civilizations orbiting this star to receive our early transmissions, and at that distance it will take at least 920 years to receive a reply. That's the Jackson equation, and be sure to subscribe to the Floreshime channel.